Hey guys, welcome to another video. Today I'm just going to be talking, we're going to go into calculus and I'm just going to talk about functions, their domains and ranges, and their graphs. So without further ado, let's just get started. A function is a machine. And what it does is it takes a set of inputs, otherwise known as x, and it transforms them. Resulting in an output y. And so in this case, we can think of x as being like some numbers 1, 2, 3, etc. And then we can think of that resulting as those values are pushed through this machine. They end up in some values like y1, y2, y3, corresponding to their input. So the function is a machine that takes an input and then it transforms it into an output. Functions can be visualized using graphs. On the horizontal axis, typically we will put the independent variable, and on the vertical axis, typically we will place our dependent variable. Because this is the vertical axis, it is often called y. So we use y for the output variable, as seen here, and we use x as our input variable, as seen here. Drawing the graph of, let's say, x plus 3, let's start at x equals 0. How can we get the function value y? How can we get a point from this information? Well, if we're using the function y equals x plus 3, we can directly infer that at x equals 0, y equals 3. So what I will do is write this in a coordinate form, typically like in the form of, I'll make a table. This is the best way to do it. We make a table. So we'll have an x coordinate and a y coordinate, and we're going to do multiple ordered pairs is what these are called. So I'll say we'll do 0, 1, and 2, and then we'll call that good. So by plugging in 0, 1, and 2, we can find the output values that this machine, the function, will produce. So y equals 0 plus 3. That results in 3. Y equals 1 plus 3. That results in 4. Y equals 2 plus 3. That results in 5. So in this instance, the machine y transforms these input variables 1, 2, and 3 to 3, 4, and 5. Similarly, by just looking at this data, you can get this formula. And we'll talk about how to do that in a later video. But right now, I'm just going to plot my points. All this means, now how do we use this data to get our coordinates? We basically just plug them into ordered pairs. We're we're going to put it in the form of an ordered pair, which is just x and y coordinates, right? So we have our x coordinate, which is 0, and we have our y coordinate, which is 3. Similarly, we have our 0 coordinate, which is, our x equals 1 coordinate, which is 1. Plugging that into the function results in a 4. Finally, inputting 2 into this machine, this function, results in an output of 5. Okay, and hopefully you're seeing a pattern here. But what these are the ordered pairs that give us the points to our coordinates. So I'm just going to do this. I'm just going to say, where's 0 and 3? Well, we're at x equals 0, 3. Similarly, 1 and 4, we just move over, go up 1. Similarly, boom. I know it's a line with a slope of 1. Also, that's good information. And so all sorts of stuff can come out of this. We can also say, what's the slope of this line? Well, I mean, you can kind of tell just by knowing about y equals mx plus b, in that m is the slope. This is your x coordinate along this axis right here, and then b is going to be the y-intercept. And that is actually the value at which the graph crosses the y-axis. That's why they call it the y-intercept, is where the graph goes across the vertical axis. And so that's how you get your coordinates, just by listing them out. Now, there is a couple of things, I guess, things to note. So we see right here that a function, from what we've learned, that it takes an input in this set, which we'll call D, which stands for domain, and it assigns a unique value in this set of numbers, which is called the range. We'll call it capital R. There will be plenty of different uses for the letter R in this class. For now, we're going to call it range. So essentially, what this is saying is the domain makes up the set of numbers that x can be. So x is within the domain in general. This is just generally speaking. Similarly, f of x is all the set of numbers or values that are within the range. And this kind of all comes together if you just sit there and think about it for a second. Okay. Now, how do we write this? what are we talking about? We've got a domain, we've got a range. So again, the domain is just all of the possible x values that can be plugged in, such that the function is defined, right? We want to keep the function defined. So we don't want to have anything like a negative under the square root, or we can, we just have to define it differently. It's not going to be x can just be anything, right? Because you can't have negative numbers under a square root. Similarly, you can't have like 1 over x where x equals 0. And this is actually the example we're going to tackle right now. So I guess without further ado, let's just get started. So if we let y equals 1 over x, and then I say determine the domain, write the set of all possible x values such that y is defined, and determine the range. All right, well, a good place to start here is the graph, right? So let's just look at the graph of the function 1 over x. So we have our x-axis and our y-axis. I should probably extend that out a little bit. So, okay, so drawing the values here, well, let's try something. So let's write our function out. Okay, and then we already know there's going to be a problem at x equals 0, right? We can't do that. So let's not choose 0 first. Let's choose 1, and let's choose 2 and 3. And let's also do that in the negative direction as well. And I'll also just label this. Okay. You know that. All right, so what is, when we plug in x equals 1, and I'm just going to, again, make a table of values here. So let's just start from the left and then go. So negative 3, negative 2, negative 1, 0, 1. We can't do 0, right? Don't even write that down. Positive 1, positive 2, and positive 3. Those are these ones to the right of the y-axis. So if we plug in y equals 1 over negative 3, well, that just equals negative 1/3, right? And so we can just write that in right there. What about 1 over negative 2? Well, that's just negative 1/2. Similarly, this is negative 1. And then you'll notice that right here, it kind of mirrors itself, and this is just for this function. This isn't for all functions, but I'm just going to write 1, 1/2, and 1/3. And so the general pattern, if we were to continue doing this on both sides, extending outwards towards infinity or whatever, we would get a pattern something like this. Let's see. Let me just plot the coordinate points, and we'll see what this kind of looks like here. And I want you to plot these as I'm writing them out so that you can see what's going on for yourself. What happens if we plug in like something really close to 0? Like what if we say 0.001? Well, y equals 1 over x, right? Which if we plug in this for x, we get 1 divided by 0.001. Well, this is just 1 over 1,000, right? So this equals 1 divided by 1 over 1,000. Division is the same thing as multiplication by the reciprocal. That equals 1,000, right? So, and similarly, if this was negative, that would just make that negative, that would be negative, this would be negative, and that would just make negative 1,000. So we can see the values of the function get really large as we get closer and closer to 0, which means that they grow very quickly as you go to x equals 0. So as you approach from the left, we end up going to this, negative infinity. And then similarly, I'm just going to kind of it goes like that. And then as we come from the right, we shoot up towards this positive infinity value. So the whole goal was to determine the domain and determine the range. Well, if we look at the graph, kind of, usually you would just plot this on a software, but I thought the practice would be nice. However, now that I'm thinking about it, that was kind of time consuming, but it is the process. So we saw that our general shape is like that. You have this vertical asymptote right here, which is the x value that the function cannot approach. All right. Or it can only approach, but it cannot be. And we can see that there's nothing really limiting us. It just cannot be 0, right? So far we just have x cannot be 0. But it seems like everything else is okay. What happens if we plug in a huge number for x? Well, it's 1 over x. If you have a large number, then that indicates that this whole thing is small, right? Because you have a large number. You're splitting that fraction up into more and more pieces, making the fraction worth less, essentially. That's why it gets so close right here in these regions, because as you get higher and higher x values, basically the function goes to 0. And you can actually just say the limit is x goes to infinity of f of x equals 0. That's how we talk about that. But x can go to infinity. There's nothing stopping it. The function is still defined. It's just a very small number. So we can say that the domain of the function, or all the x values, can be anything we want except for 0. So x is within the set of numbers such that it goes from the interval, we'll use interval notation for this, to 0, but it like softly approaches it. It cannot be 0, right? So we use these rounded parentheses. And then we use this union symbol, which looks like a capital U. And what we're doing is we're connecting these two segments. We know we can get infinitely close to 0. Like we can get really close, but we cannot get to 0. We can get infinitely close. So we have to take this segment and then take this segment, because it is not a continuous situation we have going on there. And so that means that we need two different expressions, which are two different intervals to express this. So negative infinity all the way from the left of the graph, and then we skip 0, and then we go to positive infinity. And that's our interval set notation for our domain. What about the range? What's going on here? Well, now we're basically concerned with the vertical values that the function can take on, right? So if we redraw this graph real quick, now we're concerned with, all right, well, what y values can be created from this x being within negative infinity to 0 union 0 to positive infinity. In other words, if we plug in all the x values that are valid right here into this function, 1 over x, what is the range of values that it results in? And it turns out we can kind of see, like, okay, well, from negative infinity, it's defined pretty good by this part of the curve right here. Similarly, if we start from the top, we've got a pretty good definition of, I mean, we have, it's all defined, right? And so, but can it ever be zero, right? That's the thing. So can this ever equal zero? It looks like, you might be able to, but the thing is, it never gets there. It never approaches the value 0. You just get infinitely close to it. So in this case, the domain and the range are the same. They're the same expression. But this is just purely coincidence. Yeah, they would say D semicolon, and then we would say R colon. So it can be negative infinity to 0, similarly from 0 to positive infinity again. And so that is the domain and the range of our function 1 over x. Now, what happens if we shift the 1 over x function, right? So we say, all right, let's 1 over x, let's apply the shift from algebra, from the graph transformations section, and we'll say 1 over x minus a. Let's just say a. And let's say a is a positive number. Okay, so we just have some graph. The original function was like this, where the vertical asymptote was 0, but now we're shifting, right? So we have this vertical asymptote. Let's shift it to a. A is right here. This doesn't actually cross this. You know this. Boom. So what happens when we do this shift is essentially we just move over the asymptote, right? The value for which x cannot be. In this case, x can't be a because that results in 1 over 0, and we can't have that. No. So we're just shifting our asymptote, and I will draw this in a different color. But you keep the same pattern, right? So then like that. I know I kind of showed 2 different graphs here, but this is just demonstrating the shifting property. Graphical transformation, review that. Maybe I'll do a video on that one as well in the future. I think that that's good for now. I think that that is plenty of information on functions and domain and range. If you have any questions, leave it in the comments. Also, if you want me to do anything, just leave that in the comments as well. Don't forget to like and subscribe my channel if you enjoyed it, and I'll see you guys in the next video. Thank you so much for watching.